Hey, Calc students, this is Mr. Beck. Today we're going to be talking about two different sections. First section we're going to be talking about is the area between curves, which is 6.1 in our book. And then we're going to follow the area between curves with the volume of revolution, where we're going to take a curve and we're going to revolve it around a certain axis. So just a little insight as to where we are. If you remember, we did a lot of work with integration in general. Chapter 4 is all about just integration techniques. We included some Chapter 7 material with that. So some of those integration techniques would be useful for this section, especially if we are trying to do everything by hand. One of the things that I'm going to do with today's lesson is to say, is this something that we could do by hand or not? If we could do it by hand, we should try to do it by hand, but you'll see me use a lot of the calculator to come up with a lot of the answers as well. I want to show you some of the features of the graphic calculator. So let's go ahead and get started. We're going to begin by saying, what is the area between two curves? So if you look right here, we have two functions. We have the f function, we have the g function. And if our goal is to find the area between the two curves, what we're going to do is we're going to take this over idea that let's take the area underneath the upper curve and then subtract the area beneath the lower curve. And so when we take the bigger area minus the smaller area, we're going to get the actual area that we want. So the area between two curves, you'll see that this is bounded between the x value of a and the x value of b. We can go ahead and write it together as one big integral. So the integral from a to b of f of x minus g of x now dx. So pretty straightforward, which is kind of nice because it's nice to have that kind of mentality. One of the things that I do want to focus on is we are going to create what we call representative rectangles. Now the representative rectangle here is going to be what we use with Riemann sums and infinite Riemann sums. No, we're not going to do the overall infinite Riemann sums, but the idea is if we take this representative rectangle and take it down to the x-axis, what ends up happening is we sum up all of these heights times the function value. So we'd sum up all of these heights, and we say the height of each one of these is f of x. The lower, or the height that we're going to remove, is g of x. And so you can look at this as the infinite Riemann sum of f, and I'm just going to butcher the notation here. I'm sorry for all the math purists. So the sum of all the f's times delta x minus the sum of all the g's times delta x. So I hate to butcher the notation, but let's get on with the ideas. So with this representative rectangles, actually I should have waited because it's right here. One of the things I do want to point out is anytime that we have this distance, we can measure distance as upper function minus lower function. So you're going to hear me say this multiple times today, upper minus lower, and in this case it's the f minus the g. But by looking at this as upper function minus lower function, this allows us to say, okay, we know distance is a singular distance and minus beginning, which is why we do upper minus lower. Something people always ask me, Mr. Beck, what happens if you have one function above the x-axis, one function below the x-axis? Well, let's think about this. We know that the function above the x-axis, we know that this is a positive value. When we take the integral, we find this and we get a positive value. Well, what's below the x-axis? If we take the integral, we get a negative value. And what happens when you take a positive minus a negative? You definitively get something more positive. So what this does is, in essence, this adds the two areas together. So the nice thing is, algebraically or really numerically, when you look at how the numbers work, when you take the upper function minus lower function and take those integrals, and what ends up happening is we're always going to end up with a positive value, as we should, because this is area. And then the next question is, okay, Mr. Beck, what happens if both functions are below the x-axis? So if both functions are below the x-axis, what I'm going to do is represent this by saying, okay, we still want to treat this as upper minus lower, and this was meant to extend over here. So we still are going to treat this as upper minus lower, where the upper function is going to be a small negative value, where the lower function, when we take the integral, it ends up being a much larger value. And so that resulting value that we want, which is that bounded region, I'm going to extra highlight here. So that bounded region ends up being an overall positive value because we take a small value, negative minus a larger negative. So in the end, as long as we take this and treat it as upper function minus lower function, it does not matter the orientation that we're working with because we should end up with the area. So one of the things that I do like to point out and have my students do, especially right at the beginning, I like them to graph all of this information. So this is kind of like a practicing graphing. Obviously, you can see the graphing calculator on my screen as well. So we're going to be using the technology. But whatever we can do without the technology, it only strengthens the ideas because there are going to be many, many times that you're not going to have a calculator and you're still supposed to know exactly how to approach it. And if you can make quick sketches, you're in good shape. So first things first, if I find the area bounded between y equals x squared plus 2, y equals negative x, and x equals 0, you can see that I have that whole region set up right here. So y equals x squared plus 2, make sure you know how to draw parabolas based off of the numerical pattern, 1 squared, 2 squared, 3 squared, et cetera. Hopefully you can draw y equals negative x. You can see that's the region that we're looking for. What I ended up doing was I said, okay, my upper minus lower, you can see the representative rectangle that I have here. Don't think I can highlight that anymore. The representative I have there in red, if I treat it as upper minus lower, the upper function is the parabola, the lower function is the line. So parabola minus line will give me that expression. So if I integrate that from the x value of 0 to the x value of 2, which is going to be the region we're looking for, this is one that I feel like we could do manually. And so by doing it manually, we end up with a overall answer of 26. Step number 2. So suppose we have a bounded region. Well, a bounded region means, you know what, I think we need to find our intersections. So to find the intersections, what I ended up doing with this problem was I graphed it and said, okay, what does the parabola look like? What does the line look like? What are my two intersection points? And I use those two intersection points of -2 and +2 in order to set up my integration. Well, what's my upper function? What's my lower function? We can see by the graph that the upper function is indeed the line. The lower function is indeed the parabola. So upper minus lower simplifies into this negative x squared plus 4. So then I'm going to take the integral from -2 to 2 of negative x squared plus 4. Something special that I did here, if you remember, if we take the integral of an even function from -a to +a, then what we could do is we can double that integral from 0 to a. And that's actually what I did right here. So I doubled from 0 to 2. The benefit of that is when you plug in 0 to a lot of different functions, then what ends up happening is you get 0. So big benefit. So overall, double. This is definitely one that we could do by hand as well, which is what I did. So antiderivative, plug in 2 and plug in 0 again gives us 0, so -0. We get an overall answer of 32/3. We could check the calculator, just very, very quick. If you remember, a shift plus will give us that integral, the definite integral. So let's go take the integral from -2 to +2. And if we say negative x squared plus 4, you get your differential of x, very, very important. Then we get 32/3. So life is definitely happy. Example number 3. I did end up graphing this, but I also in class, one of the things I said is, what happens if I don't really know what this is going to look like exactly in the graph? Because not too many people can immediately graph negative x squared plus 4x plus 2. You'll see that I did complete the square in order to figure out what it looked like. But I said, okay, if this is a bounded area, we know we have a negative parabola and we have a line with a positive slope. So we can assume that's what we're looking for. We could set the two equations equal to each other to figure out the x coordinates of intersection, which is what I have here, what I have here. And then how do I know which one is the upper function and which one is the lower function? Let's choose a value between 0 and 3 and say, okay, what is f of 1? F of 1 is -1 plus 4 plus 2, which gives me 5. I can count. What is g of 1? G of 1 is going to be 1 plus 2, which is 3. So that tells me the f function is above the g function, which is why it should be f minus g, or in this case, parabola minus line. Then what I had the students do in class, this is one that we could definitely do by hand as well, but throw it in the calculator, shift plus. We're going to go from the x value of 0 to the x value of 3. And then parabola is going to be negative x squared plus 4x plus 2 plus 4x plus 2, then minus the line, which is x plus 2. Don't forget our differential. 9/2 is our answer. Again, that one was one that we could do by hand, but I didn't actually do that one for everybody. On to our next problem. F of x is the square root of 3x plus 1. I did graph this by choosing some points. I chose the x value of a 0 to get the square root of 0 plus 1. I did choose the x value of 3 because the square root of 9 plus 1 was a nice point. You could look at this as this is a horizontal compression by a factor of 1/3, so we can make some additional points that way. But anyway, upper function minus lower function should be the square root function minus the line. We could see that on the graph. If you didn't know that, again, plug in x values between the points of intersection. So, long story short, upper function minus lower function, integral from x equals 0 to x equals 3, because that's where the two functions intersect each other, and we get 1.5. Now, what happens if you didn't actually know where the two functions intersected each other? If you didn't know where the functions intersected each other, we could have done this on a graph. So let me go ahead and do this as the square root, which is right here. So the square root of 3x plus 1 as f1 of x. And then f2 of x is x plus 1. So what if I wanted to find these points of intersection? Suppose they weren't nice. We can go to menu and go to not trace. Analyze the graph, find the intersection points, and it says lower bound. So lower bound from here to here. That intersection automatically comes up with the intersection, which you see is 0, 1. We could do this again. Menu, analyze graph. Let's find the analyze graph. Try that one more time. Intersection. What's the intersection point from here to here? That point, oh, I can't see it. Don't forget, if you hover over it and hold down, you can grasp it and move that point. So there's my other intersection point. So I show this because there are going to be some functions you're going to encounter, a lot of AP style problems. In fact, I think at least one of the homework problems I'm assigning has you find intersection point, which is really, really nasty. If you end up with a nasty intersection point, you can highlight it and you can use the store feature. If you remember, I taught you that in previous lessons, but you could copy, Control-C, Control-V. So Control-C. I don't think I actually copied from the other screen. But anyway, you could take that number, which in this case, 3, 4, so it was 4. And then you can go ahead and store this as a variable. So let's store it as B. So that anytime I type in B, I get 4. So like 3B is going to be 12, et cetera, et cetera. One of the benefits of using the calculator, I know I've shown this in the past, it doesn't hurt to show it one more time. So we know that f1 of x is the square root of 3x plus 1. So what if I say f1 of 3, which is one of the points that I used, should give me 4 because it's using that function. So f1 of, let's say 2, square root of 6 plus 1, which makes sense. But anyway, going back to the problems. So on example number 5, you can see on example number 5, f of x is x minus 1 cubed. And as soon as this updates itself, hopefully it's going to be sooner rather than later. On my screen, it's already shifted over. Let's try to give it a little bit of a nudge there. And still waiting. Anyway, do you know what f of x equals x minus 1 cubed looks like? We can go ahead and graph that one out. G of x ends up being x minus 1. And let me pause and get that screen back up for us. Hold on one second, please. And I'm back. So as I mentioned, we have f of x equals x minus 1 cubed. We have g of x equals x minus 1. We can see these two graphs right here. We can see that they intersect not just in 2 spots, they intersect in 3 spots. So if our goal is to figure out what the bounded area is, we are going to have to treat this as 2 distinct different regions. One of the things that we are able to do is we can call we can just use the fact that we have our function here, f of x, oops, let me do it here. We have our function here, f of x equals x minus 1 cubed. what we're able to do is we're able to say, okay, let's do this symbolically so we don't have to just rewrite all of the different equations. So from the x value of 0 to the x value of 1, we know that it's going to be the cubic function as the upper function. We have the line as lower function. So cubic minus line dx. And then the second region that we have, go from the x value of 1 to the x value of 2. This one's going to be line minus cubic. So we can write this as g minus f. Anytime you have functions that are defined as specific values, you are welcome to do this just to save on notation. I encourage this, especially when it comes to the AP test. That way you don't rewrite something and write it wrong. I also encourage this if you have a lot of different notation that you are going to use, or if you have a calculator, that you can honestly put that function in the calculator and then you can do something like what we did over here. So anyway, I did plug these into the calculator. Let me go ahead and actually type those in for us. So let's do a quick doc B. Doc B clears the scratch pad. That way I could just type it in fresh. So f of x is x minus 1, x minus 1 to the third power. Enter. f2 of x is x minus 1. So there are my two functions. I can go to this screen and I can say, okay, what is the integral? So shift plus. If I want the integral from 0 to 1 of f of x, actually that should be f1 of x. Notice how it makes it bold, minus f2 of x, because that was cubic. Then dx, that gives us 1/4, which you can see I have there as well. And then we could recreate this by saying the integral from 1 to 2 of f2 minus f1, which will also give us 1/2. Now, one of the things that we are able to do is we can use the notation that I have here, that what happens if I just want to go more quickly with this. If I want to go more quickly with this, what I could do is I could just take the absolute value of the entire function going from beginning to end. What that would do is that would turn any negative region into a positive region. And by doing the negative region into a positive region, it just evaluates it pretty efficiently. So let me show you where that is. Shift plus, we're going to go over the entire region from 0 to 2. And we'll go over here. Right next to the book is our favorite key. Our favorite key has the absolute value button right there. And this is where we're going to say f1 of x minus f2 of x. And if you notice, we get 1/2, which is what the overall answer is. Now, it doesn't matter what order we put it in. No, it does not, because whatever the negative region is becomes positive. So if I really wanted to write this as g of x, aka f2 of x, minus f of x, I should still get that value of 1/2 as well. Moving right along, I have another region here. This region is going to be a rational function bounded by y equals 4. So that bounded region that I'm looking at is just this small region right here. So if I want to find the intersection point, I could do it algebraically. Based off the graph, it was a really nice graph, but algebraically, I could say 4 over 2 minus x equals 4. So 4 will equal 4 times 2 minus x. 1 is 2 minus x. So x equals 1. That's going to be the point of intersection. So that's how I know what my upper limit is. My lower limit is x equals 0, which is what they give me. Upper function minus lower function. Obviously, we could see the graph there. If we couldn't see the graph there, we could choose a value of like f of 1/2, which will give us a number that's less than 4. So that kind of indicates what's going on. The more we can visualize the graph, and I strongly encourage you to be able to look at this and say, yes, I know what rational functions look like. The more you can visualize it, the stronger off you're going to be. Plain and simple. So anyway, this is one that I integrated by hand. So 4 minus 4 over 2x. Don't forget that when we integrate, we have a chain that we have to recall, which is why this is a positive. And then it'll be 4 plus natural log of 1 minus 0 plus 4 natural log of 2. Or overall answer of 4 minus 4 natural log of 2. Just to reiterate something, suppose I say 4 minus 4 natural log of 2. That gives me an exact value. What happens if I really want to know what that decimal approximation is? what I could do is I could hit a decimal point anywhere next to one of the numbers, and it'll turn it into a decimal for me. In this case, 1.227. Don't forget, we always go to 3 decimal places. Well, what happens if we have a situation like this? If we have a situation where we're bounded by x equals 3 minus y squared and x equals y plus 1. When I take a look at this, I go, do I know what these look like? Well, if I don't remember how to graph with respect to y, I'm in a little bit of trouble unless I say, let's go ahead and take this, solve it for y. By solving it for y, I get both the positive square root and the negative square root. So the positive square root graph, which is what I have here, that positive square root graph, if I think through it graphically, this is a reflection over the y-axis and shifted to the right 3, kind of modeled by that in case you don't remember. And then the negative square root is going to be also a reflection of the x-axis. And I can solve the x equals y plus 1 for y to get y equals x minus 1. Now, the downside to doing this approach is I now have 2 regions that I have to consider. If you notice for each region, this case and what's in green, the upper function is the line, the lower function is the negative square root. So I have line minus negative square root. Where the red region that I have there is going to be the positive square root minus the negative square root. So that's why I have the positive square root minus the negative square root. So when we do this, we could type it in the calculator and we should get 9/2. Now, obviously that's a lot of work that I really don't want to show for you right now, just because I want to keep this in much shorter form notes that I can. So what's better is, can we graph this with respect to y, which is what I did over here. So if I graph this with respect to y, what this ends up looking like is this is a negative quadratic with respect to y, which means negative quadratic is it opens downward for x. Downward for x is to the left. So then the x-intercept is 3 as opposed to the y-intercept of 3. So that's why our parabola looks like it's a horizontal parabola like so. And then x equals y plus 1. This is now my x-intercept of 1 instead of my y-intercept. And my slope, let me do this, my slope is now delta x over delta y. So really, this is just graphing inverses. It's a reverse of the mentality. Whatever was the y-intercept before is now the x-intercept. Whatever is the x-intercept is now the y-intercept. Slope is change in x over change in y. So if we do this horizontally, one of the things that we need to consider is what's our representative rectangle? That representative rectangle is a horizontal distance, or is a horizontal rectangle. So if we think upper minus lower, so which is what I have here, upper minus lower, upper for x is actually in the right direction. So this is my upper, because those are my positive x values. My lower is to the left. So one of the things we need to look at is the right curve minus the left curve maintains that upper line minus lower mentality. So in this case, the upper curve is the parabola, 3 minus y squared. The lower curve is the line y plus 1. So if we integrate that one honestly we could do by hand relatively easily. We should get 9/2 as well. Well, what happens if you have a function, you're like, I have no clue what this looks like. And I don't blame you. Not too many people know what y over the square root of 16 minus 5 looks like. That's not one of the common ones. So what can we do? We can graph on the calculator y equals x over the square root of 16 minus x. I'm going to go ahead and do a doc b just to clear it one more time. So what does y equals x divided by the square root? Let me find that. The square root of 16 minus x squared look like? What I'm doing is I'm graphing this through inverses. So there's my x over the square root of 16 minus x squared. And this is going to be bounded by y equals 0, which is going to be my x-axis, and x equals 3. So x equals 3 is going to be right here, which means that I can take the integral from 0, wrong tool, integral from 0 to 3 of our function, which ends up being 4 minus the square root of 7. Now, we could do this in the calculator, assuming we understand what that orientation looks like. We could do this on the calculator. So this is what we see in the calculator. What's actually occurring is we have a graph that sort of looks like this, and we want to know that overall area. So it's the same thing. Doesn't matter if we use X or Y, but what's important is whatever variable we use, these numbers all line up with that variable. We do have this problem right here, this AP problem where we have a region bounded by the x-axis and part of y equals cosine of x between those two x values. In this case, what ends up happening is we're separating two regions by x equals k, where x equals k breaks this smaller region is going to be, or really the larger region is 3 times the smaller region. So you can set up the problem that way, and that'll work. But if we integrate both sides, we're going to have a k that's going to be involved on both sides. Another approach we could take is that smaller region, what we have is going to be a quarter of the overall region. So that's why this is broken into like a 3-to-1 ratio. We could say, okay, this is 1/4 of the entire thing. Either way you do it, you get the arcsine of 1/2, and everybody knows the arcsine of 1/2 is pi over 6. So on to 6.2. So that's a lot of work involving area. 6.2 is what happens if we take that rectangle and we revolve it around a certain axis. So we take that area and we're revolving the entire area around the axis. Now, one of the things I'm going to do is I am going to open up the screen in Safari. I do have this link on Canvas for us. So when we take a look at this, if we are going to revolve, and what you should see, hopefully, you could, oops, wrong one. You could see that we are revolving a bunch of rectangles, and those rectangles are the Riemann sums again, revolving those rectangles around a certain axis. What this does is creates a series of disks. Well, since it's a series of disks, we go from an area of a rectangle to a volume of a disk. The volume of the disk is going to be pi r squared because it creates circles, pi r squared times the thickness, and the thickness of this is actually dx. So if we do larger and larger numbers of disks, what you can see is we get a better approximation of the actual volume, which makes sense because we had the larger and larger number of rectangles creates a more appropriate area. There's a larger number when we revolve it creates a better volume. So that's what's represented, what we see right here. Now the thickness of each disk in this case is dx. You can see the representative rectangle that we had before. That's what's being revolved, and that is going to be my overall radius. So the radius, when we revolve it, ends up being pi r squared. That pi r squared is the area of the circle times the thickness, dx, and we sum up all of those together to get our formula, the pi times the integral from a to b of our radius squared dx, where that radius is going to be that distance from the function to the axis. Plain and simple. Now, what happens if it's a vertical axis revolution? We will do this by putting everything in terms of y, kind of like the last problems that we did. So x equals some function of y, some function of y. So then we get pi r squared, and this is found by right minus left, just like we did before. This one, I never finished it, upper minus lower. So you're gonna hear me say upper minus lower and right minus left quite a bit. So let's take y equals the square root of sine x. Y equals the square root of sine x. What I like to do is I like to draw on that representative rectangle. So I could, and that representative rectangle could be shifted anywhere along this curve. It would still always be the function height minus 0 in this case. So my radius is square root of sine x minus 0, which simplifies to that expression. Life is good. And then we will take our volume from 0 to pi. The reason why it's 0 to pi is because those are the bounds on my graph. 0 to pi. Pi r squared dx. A lot of times people will put the pi on the outside. I absolutely have no problem with that, and you'll see me do that quite a bit too. The downside of that is I've had too many students forget their pi's as they're writing it. So just please, 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 please be very, very careful. So square root of sine squared is just sine. This is one we could do by hand. The integral sign is negative cosine. Plug in our pi minus plug in our 0, and we get 2 pi overall. Problem number two. Problem number two, we can see this is revolved around the x-axis still. So we draw a representative rectangle. Upper function is 4 minus x squared. Lower function means what's the axis, which is 0. So that's my radius. And I just did this one in the calculator. Pi times the integral from 0 to 2. And the reason why we're going from 0 to 2 is because that's our bounded region. I could do more and more of these in the calculator, but I already showed you how to do a couple. Let's do this one in the calculator together. This one is in terms of y. So if we're doing this one in terms of y, we have to have our horizontal representative rectangle. So right minus left is going to be the parabola minus 0. And so, as I said, I was going to do this one in the calculator. Let me go to this screen. We will have pi, which pi is down here. Pi times the integral, so I'll do shift plus. Now my limits of integration are going to be from the y value of 1 to the y value of 4, we see there. So y value of 1 to the y value of 4. If we do right minus left, it's going to be the parabola, as I mentioned, negative y squared plus 4y. So parabola, let me type that in properly. So parabola, and then minus the axis, which is 0. And put this in terms of y, and you can see, oh, what did I do wrong? I forgot to square it. It's like something's not right here. So my radius squared, kind of an important thing, Mr. Beck. Oh, shoot. And I'm just gonna close this off right here. And now square it. There we go. We have a more appropriate answer. All right, on example number 4, I have a lot of students who are like, hey, can we just do this a different way? And I'm like, no, we need to make sure we know how to set it up properly. So in order for us to do this with respect to y, first we need to solve our equation for x. And the steps involved, y squared is 16 minus x squared. So x squared is 16 minus y squared, and we take the square root. And just so you know, this is the positive square root of 16 minus y squared. This side would have been the negative, oops, not that side. That side would have been the, no, I was right the first time. So this is x equals the negative square root of 16 minus y squared. But anyway, I digress. So we throw that into the calculator and we get 128 pi over 3. Now, as a quick check, what I like to do with this as a quick check is, if we indeed revolve this, we end up with a hemisphere. So that hemisphere, we know that the volume of a sphere is 4/3 pi r cubed. So the radius of this circle ends up being 4. So the radius of the sphere is 4. So the volume is going to be 256 pi over 3. But it's a hemisphere, so we have to divide it by 2. And we do get 128 pi over 3, which is what we should have. Next problem. This is going to be our first one where we're not revolving it around y equals 0. In this case, I'm revolving it around y equals 2. Something that's hidden here is, first thing we have to do is find those intersection points. So I set 2 equal to the function that I have here. And the x values that I get are positive, negative square root of 2, which turn into my limits for my integration. Now, this representative rectangle does go from function to axis. So the upper function is 4 minus x squared over 4. The lower function, which is my axis, is 2. Simplified is what I put in here as pi r squared. So I have that as pi r squared dx. And then what I did here is, by squaring it, I turned it into an even function. So I can now say 2 pi going from 0 to 2 squared to 2, et cetera, et cetera. I believe I threw this one into the calculator, and I get 128 squared root of 2 over 15 pi. I would say that's definitely a calculator problem. So then we get the washer method. Now, what the washer method is very, very similar to what we did with the area between two curves. So the area between two curves, what we ended up doing was we took an overall, just write this down somewhere, we took an overall area and we subtracted that smaller area to get the area that we wanted. Very poorly represented in my opinion. Anyway, What we're doing with the washer method is very similar, where now we have a representative rectangle that there is a gap between the axis of revolution and the solid that we're revolving. So what we end up doing is we take the overall volume, which comes from the outer radius, that overall volume, which is pi r squared, and then we're going to subtract out, so we're going to subtract out the inner volume, and that volume is pi little r squared. So the overall volume minus the inner volume ends up getting rid of that hole really in the center. So we could write this as two separate functions, pi capital R squared minus little r squared, or we can join that in together into one overall integral. So I'm going to take that same scenario that I had before, but this time I'm going to revolve it back around y equals x, or sorry, y equals 0. So revolving around y equals 0 does two things. Number one, it creates a gap, and that gap means we're going to have to subtract out something. What we're going to end up subtracting is we're going to subtract out that inner into a cylinder, by the way. So the overall outer radius is 4 minus x squared over 4 minus 0 because it's upper minus lower still. So upper minus lower. So the inner radius is upper minus lower. In this case, it's 2 minus 0. So we have pi outer radius squared minus pi inner radius squared. And then you can see I did a quick amount of simplifying, and I get either one of these two solutions. One of them is a decimal, one of them is exact. On example number 7, what I like about example number 7 is it really highlights all the distinction between what happens if we move this region around. So this is a quick sketch that I did, that I know that I have a parabola, y equals 6 minus x squared, or 2x minus x squared. I could have typed this into the calculator to see it. I also have the line y equals x plus 6. So what I ended up doing with this is I just kind of like remodeled that region, but if I'm revolving around the x-axis, I end up having the gap here, and that gap, it creates something that we're going to have to subtract out. So my outer radius is upper function minus the axis. My inner radius is the lower function, the line, minus the axis. So pi capital R squared minus little r squared. And I threw this into the calculator to get 243 pi over 5. Now, if I'm revolving this around y equals 3, what I end up doing is, like the last one, if I revolved it, you can see that this ends up being a very, very big region that gets revolved. For this one, ends up being a much smaller region that gets revolved. So it turns into almost like a cone, or at least the inner part's a cone, where the outer part is like an overall bowl-ish kind of shape. But anyway, this case, it's going to be upper function minus, when I treat this, once again, I have a gap here, upper function minus axis. Lower inner radius is lower function minus the axis. You can see that I simplified pi capital R squared minus pi little r squared, and threw it into the calculator to come up with my answers. This one is a little bit more fun because what happens is the axis is above that region that we're revolving. The axis is above the region that we're revolving. This time, the upper minus lower is going to be the axis minus, well, for the outer radius, it's the axis minus the line. So my outer radius is that big one, axis minus the line, so 8 minus x plus 6. The inner radius is what we see here, which is the axis minus the parabola. So outer radius simplifies to 2 minus x. That's what this one is. So pi capital R squared minus pi little r squared. Throw it in the calculator to get the answer. Example number 8. This case, if I draw my representative rectangle, we can see that we have the gap. So my outer radius is going to be the square root graph. My inner radius is going to be the y equals x squared graph. This is one that I felt like we could do on our own. So outer radius is square root minus 0. Inner radius is x squared minus 0. So I'm going from 0 to 1. How did I know I was going from 0 to 1? Set my functions equal to each other and solve. Pretty easy. This one, as I said, I did manually. So this ends up being just x minus x to the fourth, antiderivative, plug in 1, plug in 0, I get 2 pi over 5. Example number 9 is our last example. If we're revolving this one about the y-axis, what that indicates to us is we have a horizontal axis revolution. This one has to be broken into 2 parts, unfortunately. So the lower part goes from 0 to 1. Outer radius, or like upper function, in this case, right function is always going to be x equals 1. The left function here is going to be x equals 0. So 1 minus 0 is going to be my radius. So basically, this turns into pi y. That's because pi r squared, the radius is 1. So pi r squared times the height is going to give us this part of the cylinder. Now the second portion is where we have a washer. So the bottom part is really more of a disc, where the top part is more of a washer, where we have the outer radius is going to be 1, which is what we see here, minus, and then, oops, I guess it's right here, my apologies. So the outer radius is 1 minus 0. The inner radius is going to be our function in terms of y, which is what I did over here. So this is the positive square root. So the inner radius is going to be that square root graph minus 0. So pi capital R squared minus a little r squared for this upper region. You can see the math that I did there. And then add those two regions together to get 3 pi over 2. Hopefully this was very informative to you. One of the biggest things is for you to be able to visualize and articulate what's my outer radius, what's my inner radius. Radius is always found by upper minus lower. So that upper minus lower could be function minus axis or axis minus function based off on which one is upper, which one's lower. If we revolve around a vertical line, same thing, right minus left. That could be function minus axis or axis minus function based off of which one is the right function and which one is the left function. And you'll get some extra practice with this tonight. So good luck all the Calc students, and I will see you later.